Okay, I'm going to make it clear right now, I have no intentions of actually doing this problem fully to completion. This, more than any other problem I've seen in this textbook so far, is almost mean-spirited in sort of just how complicated the actual system of equation gets to solve it. But before we actually get to that point, let's just start by finding out how to set this up first. So we're looking for the transmission coefficient for the previous problem. So once again, we have a double delta well. And this time, since we want the transmission coefficient, we're looking for scattering states. So scattering states have the general solution of complex exponentials. As we've solved it earlier in this section, the general solution is going to look something like psi of x being a piecewise that equals a e to the ikx plus b e to the negative ikx, c e to the ikx plus d e to the negative ikx, and e times e to the ikx plus f e to the negative ikx. This is when x is less than negative a, this is when x is between negative a and positive a, and this is when x is greater than a. So if we graph this, what we have is, so what we have is our delta wells, right, that look something like this. So this is at x equals negative a and x equals positive a. And then we have our sort of the incoming particle. So we have a forward wave going from left to right in AE to the ikx. We have a backwards wave going from right to left with BE to the negative ikx. Similarly, CE to the ikx describes a wave in the middle going from left to right, and then DE to the negative ikx is a wave in the middle going from right to left. And then finally on this side we have e to the ikx, and then f e to the negative ikx. So first things first, automatically we're going to assume that our particle is incident from the left, as we've done earlier when actually deriving out the delta well. So if we do that, then f e to the negative ikx just is impossible, so we automatically get rid of this term. And we enforce that f is effectively 0, therefore sort of making our system just a little bit simpler. And from this point, if we want the transmission coefficient, we once again start looking towards relative probability. So if this was a single potential well, then we already know how to do the transmission coefficient for that. We just take the magnitude of sort of c squared over so if there wasn't a well at x equals positive a, the transmission coefficient would go as like c over a magnitude squared, as we've seen earlier on. The difference here is that we have two potential wells. So when we have two potential wells, all things considered, the actual process is still the exact same, because ultimately ae to the ikx represents the incoming particle, be to the negative ikx represents the particle getting reflected off of the first well, ce to the ikx represents the particle making it through the first well, de to the negative ikx represents the particle making it through the first well and it getting reflected backwards, and then big E times e to the ikx is the probability of making it through both potential barriers. So sort of even though we have these two additional sort of cases in the middle here, they don't actually matter in the grand scheme of things, because they're not what we're focusing on. We're not focusing on like intermittent behavior in between these two wells. We're focused on whether or not this particle can make it through both wells and keep on going onwards to x equals positive infinity. So the transmission coefficient here is effectively unchanged. It is still effectively just big E over a magnitude squared. So this is pretty much all we have to find. So we have to find the magnitude of e squared over a squared. And to do this, we do it in the exact same way as before, sort of where we set up our boundary conditions and then we solve the system of equations. So let's set that up. So first off, obviously we have continuity. So at x equals negative a, we have a e to the negative ika plus be to the positive ika has to equal ce to the negative ika plus de to the ika, and this is when x equals negative a. Similarly, at x equals positive a, we have ce to the ika plus de to the negative ika being equal to big E times e to the ika. So these are our two continuity conditions. The second thing is discontinuity, as before, in d psi dx when potential is equal to infinity. So once again, the thing here that we follow is that the difference in the derivative at some critical point x is equal to negative 2m alpha divided by h bar squared multiplied by psi at that critical point. So if we have psi of x looking like this, then if we want d psi of x, well, d psi by dx is going to be, let's see. Well, maybe I want to write the constants in the front first. So a I k e to the I k x minus b I k e to the negative I k x. And then we have c I k e to the I k x minus d I k e to the negative I k x. And then finally e I k e to the I k x. So if we take all these and move them down here, oops. Take all these and effectively move them here, then what we're going to get is, let's see. So starting with the first two, so this is when, okay, x is less than negative a, x is between negative a and positive a, and then x is greater than a. So let's start with the discontinuity at x equals negative a. Final minus initial, so we do c I k e to the at negative a, so negative I k a, minus d I k e to the positive I k a. Subtracted by the final, which is, so final minus initial, so this is final, subtracted by initial, so this is going to be minus a I k e to the negative I k a plus b I k e to the positive I k a. And this is equal to negative 2m alpha over h bar squared, and then psi of a. So for psi of a, we can choose either of these. For simplicity, I'm just going to choose, the first one with a and b. So this is going to be multiplied by AE, once again, evaluated at negative A, so negative IKA, plus BE to the positive IKA. And this is condition 1. Let me just double check that everything's right. DIKE to the IKA minus AIKE to the negative IKA plus BIKE to the IKA. Yeah. Okay, and then finally, the condition, the discontinuity in d psi by dx at x equals positive a, which is final EIKE to the IKA, minus initial, which is minus CIKE to the IKA, plus DIKE to the negative IKA. And this is equal to negative 2m alpha over h bar squared times psi at positive a, which in this case we're just going to use the single term here, e times e to the ika. Okay, so now let's sort of get all of our boundary conditions together. So we have our continuity in psi for the first two conditions, and then we have our discontinuity in the derivative of psi at those same boundary conditions. Okay, now our goal at this point is then pretty much analogous to 2.27. We want to eliminate C, D, and B, because this is, let's see, A, B, C, D, E. This is a system of 5 variables, and we only have 4 equations. So the problem is we can't solve this because we only sort of have we only have 4 equations. We can't solve this completely. We can only at most solve this and get it in terms of purely 2 variables, but that's exactly our goal, because remember, we're trying to get the transmission coefficient, which is in terms of two variables, E and A in this case. So what we're trying to do is basically we want to redefine B, C, and D purely in terms of A and E, and then take the ratio of that and take the magnitude squared of that to get our transmission coefficient. I'm not going to do that, because this one, once again, as I've said before, is sort of almost like in a mean-spirited way, almost, just how complicated this gets. Complex exponentials do not cancel out very nicely, and the final answer is absolutely this disgusting, horrendous mess of an equation. And even with the answer sheet by my side, I was not able to get the right answer even after like 2 days straight of working on this. So honestly, it's just not worth it. This is what the final transmission coefficient is. It's a horrible looking, disgusting mess of a solution. Hang on, I made this really disgusting looking. Yeah, this is the final transmission coefficient, and this is really long, but the sort of the initial ratio of just E over A without taking the magnitude squared is even longer, and it's just not worth it. Realistically, if you actually were to do this problem, you would just plug this final result into like Mathematica and try to find what A over E is. And it would just basically do everything for you. There's just too many complex exponentials that have to be factored in. It's too easy to make mistakes. It's just not worth it. So I'm going to leave it here, and I'm going to say that this is how you set it up. And from this point, it's just a matter of plugging this into some sort of program in order to solve the system of equations for you.